Assalamu alaikum and good day everyone. This work was authored by Mr. Uday Wazmi Abood and Dr. Mosheb Lazim Shawandi, presented by Mr. Uday Wazmi Abood. I am a student master, Computer Science, Tikrit University, Iraq. Today I am going to introduce my work, which is SDA+, improving the performance of the system determine algorithm, SDA, of the switching between AES 128 and AES 256, MOLAZ method. In this presentation, I'm going to start with the introduction, the motivation and challenges, the objectives of the research paper, the study plan, the system application, the results and discussion, and finally the conclusion. Motivation: in the age of digital communication, the secure transmission of data over networks is paramount. In the face of growing cyber threats and attacks, cryptography plays a pivotal role in safeguarding digital assets, networks, and critical infrastructure. Cryptography ensures that data exchanged between parties remains confidential and is not intercepted by unauthorized entities. Confidentiality of sensitive information is one of the primary motivations for cryptography. Cryptography is used to protect data at rest, ensuring that stored information remains secure and inaccessible to unauthorized users or attackers. This is essential for safeguarding databases, files, and sensitive information on devices. Challenges: the data is encrypted with several algorithms, such as RSA, DES, and others. They all have vulnerability points, which represents a difficult choice for the user. Cryptosystems are essential for protecting data at rest and in transit. Whether it's encrypting files on a hard drive or securing data during transmission over the Internet, cryptography plays a critical role in safeguarding information. The aim should be to strike a balance between the time of implementation and the complexity of the algorithm used. Reducing the time it takes to implement encryption algorithms and increasing their complexity is a difficult task. In the research paper, main objectives were identified to guide the study. Firstly, investigating the academic literature related to the mechanisms of implementing the AES algorithm, with a focus on the academic literature that uses the parallel programming technique. Secondly, designing a system determined algorithm plus, SDA+, that defines a mechanism for using two keys of the AES algorithm, segments the target message or text into 3 blocks, creates special keys corresponding to each segment, observes the encryption or decryption process, aggregates the segments that are completed, and finally saves the output file to an appropriate storage location. Thirdly, testing and evaluating the proposed system. Overall, these objectives provide a clear and organized framework for the research paper, which ensures that the study is focused and purposeful in its approach. The study plan included several critical steps to achieve its aims. First, the systematic review process involves conducting a comprehensive examination of all available evidence related to the problem of the paper at hand, which is an essential step in building a strong and solid foundation based on current knowledge. Secondly, a new encryption system has been designed based on the AES algorithm, which will greatly contribute to protecting data from cybersecurity attacks or Trojan attacks. Thirdly, developing the system determined algorithm plus, SDA+, to switch between the two keys, 128 and 256. Finally, conduct experimental evaluations of the system to determine its efficiency and effectiveness. These evaluations provide insight into the new encryption system and its effective contribution to data protection. A new MOLAZ plus encryption system that uses two keys, 128 and 256, bit for the AES algorithm, and special keys are automatically generated by the SDA plus algorithm in the MOLAZ plus system. A multi-MOLAZ by system determined algorithm plus, SDA plus, segments the plaintext into 3 segments, then encrypted these 3 segments by the two, 128 and 256-bit, AES algorithm keys, with special encryption keys correlating to each segment, automatically generated by SDA+. The entire process is carried out in parallel simultaneously. The SDA+ algorithm observes the implementation of encryption on each of the 3 segments, and then after they are all completed, it collects those segments into one file. The encrypted file is stored in the location previously specified by the user. When the system sends messages for encryption, SDA Plus splits messages into small messages or files and distributes them to 3 queues of encoders that work in a MOLAZ method. The system waits for a subsystem signal to complete the task and then sends it to the encrypted texts. SDA Plus creates a status file indicating the status of encryption operations. Sub-applications, upon completion of the task, change their status from processing to completed. Through the interface form, the system conveys the current status of each operation and its overall progress. The events being monitored took place in real time. All SDA Plus actions, such as segmentation, running sub-applications, and aggregation, are presented through a graphical user interface, GUI. The MOLAZ Plus system is an innovative and very effective way to address data protection challenges. Results and discussion. The efficacy of the MOLAZ Plus method and its enhanced iteration employing SDA Plus was assessed in terms of their analytical capabilities for a text file measuring 2.07 megabytes. The table presents a comprehensive summary of the sample characteristics, which are crucial for comprehending the findings derived from this analysis. The comparison aims to determine which method achieves high performance with less memory and faster CPU processing speed. Therefore, decreasing the system's utilization of the maximum heap size improves the system's stability. When comparison between the use of heap in MOLAZ and MOLAZ Plus will see use heap in MOLAZ Plus less than use heap in MOLAZ, which the max heap equals 14.25 MB, user heap of MOLAZ was 13.6 megabytes and user heap of MOLAZ Plus was 6.421 megabytes. Therefore, MOLAZ Plus is more stable and high performance than MOLAZ when using CPU performance test and memory analyze test. When comparing surviving generations and relative time spent in GC in MOLAZ and MOLAZ Plus, SDA Plus, the relative in MOLAZ Plus, i.e., relative time spent in GC, %, was 0.1%, will be smaller than the relative in MOLAZ, 0.6%. With the max relative equals 0.6% and 2%. When applying the CPU performance test and the memory analysis test, the processor in MOLAZ Plus performs more consistently and at a higher speed than the processor in MOLAZ. When comparing thread and loaded classes in MOLAZ and MOLAZ Plus, relative in MOLAZ Plus is smaller than relative in MOLAZ, with the max relative equals 112,920 to 132,573. As a result, when the CPU performance test and memory analysis test are used, the processor in MOLAZ Plus performs more consistently and at a higher speed than the processor in MOLAZ. Conclusion: MOLAZ Plus' approach involved integrating both algorithms AES 128 and AES 256 to leverage each algorithm's strengths and subdivision of the encryption or decryption task into distinct sub-applications of the MOLAZ method, which can be executed concurrently. The act of carrying out a system through the analysis of CPU performance and memory tests, and the examination of results from various cases, it is determined that MOLAZ Plus exhibits superior speed and safety. Consequently, it can be argued that MOLAZ Plus exhibits superior qualities compared to MOLAZ. MOLAZ Plus is one of the new and innovative ways to protect data security. It is a step in the right direction to keep pace with the security development of the digital system. Thank you for your interest, and if you have any questions, you can write to me at the email address shown in front of you.